Today we will study about linear programming problem or linear programming model. So before moving on to linear programming model or problem, we will learn what a formulation is. So in any decision making environment, model formulation is very important because it represents the essence of business decision problem. Now the term formulation is used to mean the process of converting the verbal description and numerical data into mathematical expressions, which represents a relevant relationship among the decision factors, objectives, and restrictions on the uses of resources. Now, apart from formulation, now you have to learn what linear programming is all about. And linear programming is usually denoted by LP, and it is a mathematical modeling technique which is useful for economic allocation of scarce or limited resources such as labor, material, machine time, warehouse space, capital, energy, etc., to several competing activities such as products, services, jobs, etc., on the basis of a given criteria of optimality. Now, the phrase scarce resources means the resources that are not in availability during the planning period. The criteria of optimality is generally either the performance, return on investment, profit, cost, utility, time, distance, etc. I hope you all remember about George B. Dadsing. In the last class, I have mentioned his name. So, while working with the US Air Force during World War II, he developed this technique primarily for solving military logistics problem, but now it is being used extensively in all functional areas of management, airlines, agriculture, military operations, education, energy planning, transportation planning, and scheduling. Even though these applications are all diverse, all LP model consist of certain common properties and assumptions. So before linear programming modeling techniques applied for solving a real life decision problem, the decision maker must be aware of all the properties and assumption. So with saying that, we will move on to the general structure of linear programming problem. And before moving on to the general structure, let's break down the word linear programming. So let's have a look at what linear is all about. Now, the word linear refers to a linear relationship among the variables in a model. Thus, a given change in one variable will always cause a resulting proportional change in the other variable. For example, doubling the investment on certain project will exactly double the return, the rate of return. Now, what is programming? Now, programming refers to modeling and solving a problem mathematically in the context of operations research that involves the economic allocation of limited resources by choosing a particular course of action or strategy among various alternative strategies to achieve the desired objective. Now, the usefulness of this technique is enhanced by the availability of several user-friendly software such as Tome, Tora, QSB, Plus, Lindo, etc. However, there is no general package for building an LP model. Model building is an art that improves with practice. A variety of examples will be provided during this semester. So now let's move on to the structure of a linear programming model. So the general structure of an LP model, it has basically three elements. Now what are those three elements? The first element is the decision variable, second the objective function, and third the constraints. Now, let's have a look at the decision variables. We need to evaluate various alternatives in the sense course of action for arriving at the optimal value of objective function. So obviously, if there are no alternatives to select from, we do not need a LP or linear programming. The evaluation of various alternatives is guided by the nature of objective function and the availability of resources. For this, we pursue certain activities which are also called as decision variables, and they are usually denoted by x1, x2, etc., xn. The value of these activities represents the extent to which each of these is performed. For example, In a product mix manufacturing, the management may use LP or linear programming to decide how many units of each of the products are to be manufactured by using its limited resources such as machinery, money, material, etc. Now, the value of certain variables may not be under the decision maker's control. If values are under the control of the decision maker, then such variables are said to be controllable, otherwise it is said to be uncontrollable. Now, these decision variables usually are interrelated in terms of conception of limited resources, and in an LP model all the decision variables are continuous, controllable and non-negative, that is x1, x2, etc. up to xn are all greater than or equal to 0. Now let's have a look at the objective function. Now, the objective function or the goal of an LP problem is expressed in terms of a decision variable to optimize the criteria of optimality, which is also called as a measure of performance, such as profit, cost, revenue, distance, etc. In general, it is represented as optimize or optimize. That means optimize, in the bracket I have given it as maximize or minimize a certain linear function, as the linear function is denoted by z, and that is equal to c1 x1 plus c2 x2 plus etc. cn xn, where z is the measure of performance variable, which is also the function of x1, x2, etc. xn. The quantity c1, c2, etc. cn are called the parameters that represent the contribution of a unit of the respective variable x1, x2, etc. xn. The optimal value of the given objective function is obtained by either using the graphical method or a simplex method. Now, these two methods will be studied later. Now, this is the general format of a linear programming problem. Now, the next point is regarding the constraints. Now, what are constraints? There are always certain limitations or constraints, as we say constraints, on the use of resources. Example, labor, machineries, new materials, space, money, etc. So that limit the degree to which an objective can be achieved. Such constraints must be expressed as linear equalities or inequalities. The solution of an LP model must satisfy all these constraints. Now let's move on to the general mathematical model of a linear programming problem. So the general LPP with n decision variables and m constraint can be stated in the following form. And here we have to find the value of x1, x2, etc. xn so as to optimize the bracket maximize or minimize. Your objective function is given as z is equal to c1 x1 plus c2 x2 plus etc. cn xn, and this is subject to certain linear constraints which is given on the right hand side, where I have written the constraints as a11 x1 plus a12 x2 plus etc. a1n xn, which can be, these constraints can be less than or equal to or greater than b1. Similarly, you can have more than one constraints there. So as I said, you can have m constraints, so m equations. Okay, so m inequalities. Okay, so that is what is written on the left hand side. Now this formula or this formulation can be expressed in a compact form using a summation sign. That is, instead of writing optimize max or minimum in the above slide, on the previous slide we have written as z is equal to c1 x1 plus c2 x2 etc. Instead of that, you can write it in a compact form like z is equal to summation j is equal to 1 to n cj xj. This is called the objective function, and then this subjective function is subject to some linear constraints. So the constraints also I have written in a compact form: summation aij xj less than or equal to greater than or equal to bi, where I takes the values from 1 to m, which is the number of constraints that we use. Then xj's are always non-negative, where j takes the values 1 to etc up to n. Now here the Cj's are the coefficients representing the per unit contribution of the decision variables. Now regarding AIJs are called as the technical coefficients or the input-output coefficients. This AIJs can be positive, negative or zero. And regarding BIs are the total availability of the ith resource. So that was a general formulation, or general formulation in the sense mathematical formulation of a linear programming problem. So this was a little bit of theory that we have gone through right now. Now in the next class we will discuss a problem, so you will understand it in a better way. Thank you.